In this lecture, we will be looking at Gauss quadrature that we implement to a typical integral as well as improper integrals. So if you recall on what we've learned so far with regards to numerical integration, with the Newton-Cotes method such as trapezoidal and Simpson's one-third and 3/8 rules, the integral interval that we do for each segment has equal width of h. Okay, and when we define this value of h, the location of the base point is actually fixed at the ends of your segment. So by what I mean by that is, if this is the axis of x, when we define the width of each segment h here, the base points is always at the starting point and the ending point of each individual segment. Now with Gauss quadrature, which is also a numerical integration technique, the interval is set can be of non-equal width, but more importantly, the base points that we choose are not at the endpoints of each segment. So there is a benefit to having the base points not located at the end of the segment. So the way I can illustrate this to you is to use a comparison between trapezoidal rule and Gauss quadrature. So with trapezoidal rule, you know that if you have an integral from a to b and you want to perform it over one single segment, what you do is you draw a straight line like this, and a and b here would be your base points, because this then would be the width of your segment h. So if you do your integral, then the integral will be the area under this line here, such that anything that is in red here is your truncation error. Now for the same curve, if you perform your Gauss quadrature, what is different between Gauss quadrature and all the Newton-Cotes method that you have is that the base points, like I've mentioned earlier, is not located at the endpoints. Instead, they are located somewhere in the middle of your integration domain. So if you're asked to integrate from a to b like this, your base points are basically defined somewhere in the middle. So why is this useful? This is useful, for example, if you have a straight interpolation, you can see that the region in blue that I sketch here would have a truncation error that is either positive or negative depending on whether the value is larger or smaller. So in the case if we define a truncation error for the interpolating function is greater than the actual function to be positive, the region in blue here would be positive and the region here in red will be negative. So when you actually sum up the truncation error, the difference in the signs of the truncation error would actually reduce the total error within your numerical solution. So by having equal width, you're not able to do that, such as this example over here. But with Gauss quadrature, where the base points are actually located not at the end points, you're able to obtain a more accurate numerical integration solution than what you would get for Newton-Cotes method. So with Newton-Cotes method, such as trapezoidal rule and Simpson's one-third, the integral can be written of the form like this. So you have an integral from a to b of your function f(x), and in general term you can always write it as a summation of the values of f evaluated at certain point x and multiplied by the coefficient c, where c basically has some form of a repeated pattern. For Gauss quadrature, the way we write the general form of our Gauss quadrature is from an integral from -1 to 1 of fx dx, and this integral can be written as the summation from I equals to 1 to n of ai f evaluated at xi. So what are ai? Ai are basically coefficients, just like what you would have for your Newton-Cotes, and xi are basically points that you want to evaluate your function f. So the question right now is, what should we choose for the values of a and what should we choose for the values of f in order for us to have this statement here to be satisfied? Now, to answer this question, i.e. to answer what is the best value for values for a and what are the best values for x, is not going to be straightforward for all functions f. Okay, you cannot write this left hand side to be equals to the right hand side for any generic function of f. So to simplify our procedure, we are going to assume that the function that we want to integrate fx is of a polynomial basis function of order 2n-1. So n represents the number of points that we have when we perform our Gauss quadrature. Alright, and we assume that the function f is a polynomial basis function. So a polynomial basis function in this case assumes that fx can be 1. So y1 would basically be similar to x to the power 0, so that would be a 0th order term. So it can be fx is equals to x, which is a first order term. It can be x squared, x cubed, all the way to order 2n minus 1, which is your x to the power of 2n minus 1. Or it can be a linear combination of this. So the linear combination here can be of 1 plus x squared, for example. So it's a linear combination of 1 and x squared, or it can be x squared plus x5. So we assume that the fx that we want to integrate in our general form here is of a polynomial type equation. Okay, so if it's a polynomial type equation, then we'll have the integral, which I'm going to rewrite it here again as the integral from fx dx, and this is basically the summation of I equals to 1 to n of ai f at xi. So the key thing to see here is that rather than in your Newton-Cotes method where the integral is from a to b, where a and b are basically any general term, the integral that we write for our Gauss quadrature is from minus 1 to 1. Okay, so if it's from minus 1 to 1, the type of Gauss quadrature we call this is known as the, okay, it's already written here, it's known as the Gauss Legendre quadrature. Alright, so how then now do we find the unknown coefficients a and the unknown points xi here for functions that are written in terms of this polynomial basis function? So let's make things simple. Let's say we consider a 2-point Gauss quadrature. So again, we need to do our integral from minus 1 to 1 of fx dx, and if you're going to use a 2-point Gauss quadrature, we will have the summation from I equals to 1 to 2 of ai f at xi. And because we have two terms, we can easily write this as a1 f1 plus a2 f2. So from okay, so instead of writing f1 and f2, maybe let me write it as f at x1 and f at x2. So in this particular one equation, you can see that you have a total of 4 unknowns. So the 4 unknowns that you have are basically a1, a2, x1 and x2. The function f is going to be given to you because that is the function that you want to evaluate. So you have one equation containing 4 unknowns. We basically need 4 other equations in order for us to be able to solve for these 4 unknowns. So because we have already assumed that the function f that we want to integrate can be any of this form or a linear combination, let's take the 4th simplest form, in which case we assume that f is going to be equals to 1, x squared and x cubed. Okay, so for the case where f is equals to 1, what we have from our equation, so from our equation earlier we have f1 f at x1 plus a1 f at x1, a2 f at x2 is equals to our integral, let me get rid of this, fx dx. So if fx is equals to 1, then from this expression here we will have a1 plus a2 is equals to the integral from minus 1 to 1 of fx, which is 1 dx. So this is essentially equals to 2. So this is one equation right there. Now if we go for the second term, which is fx is equals to x, then on the left hand side here you have a1 f at x1, and because f is equals to x, so f at x1 is simply just x1, and then you have a2, f at x2 is simply a2, and on the right hand side you have minus 1 to 1 of f dx, and this can be calculated to be equals to 0. So you get a second equation there. Now the third equation will be the third basis function, or third order basis polynomial, which is x squared. So you have fx is equals to x squared. So again, if you set up this equation, you have a1 is equals to x1 squared, a2 is equals to x2 squared, and if you calculate this integral, you will find that this is equals to 2 over 3. So finally, if you let fx is equals to x cubed, you will show that a1 x1 cubed plus a2 x2 cubed is equals to the integral of x cubed from minus 1 to 1, which you can calculate this to be equals to 0. So in the end, what do we have? From here we have 4 equations which are given by this, this, and this. You have 4 equations and you have 4 unknowns, which are a1, a2, x1, and x2. So with these 4 equations, you should be able to solve for these 4 unknowns. Although you have to take note that here we are dealing with a system of non-linear equations instead of a system of linear equation. So you cannot use, let's say, Gauss elimination to find it. So the way to find it will be a lot more less straightforward than what you would do if you have a system of linear equation. But in principle, having these 4 equations and having these 4 unknowns, you can actually solve them, and you can show that a1 is equals to a2, which is equals to 1, and you can show that x1 has a value of minus 1 over square root 3, and x2 is 1 over square root 3. So what this means is that from our earlier equation, where is the equation? Yep, this is the one. From our earlier equation, we have the integral of fx from minus 1 to 1 can be written as this. Okay, so we have minus 1 of fx dx can be written as the summation from I equals to 1 to 2 of ai, f, and xi, and we know that this is equals to a1 f1 plus a2 f2. So since a1 is equals to 1 and a2 is equals to 2, we can easily call this function f evaluated at 1 over square root 3 plus function f evaluated at 1 over square root 3, because f1 and f2 are basically f at x1 and x2, and x1 and x2 are basically obtained from here. So this equation that we write here, where the integral from minus 1 to 1 of fx dx is equals to this, tells us that we can integrate exactly up to a third order polynomial using only 2 points, or evaluating the function at these 2 points here. Okay, so why is it that we can evaluate third order polynomial? Because when we when we obtain the values for a1, a2, x1, and x2, we obtain it for polynomials up to third order. So this statement tells us that we can evaluate an integral using Gauss quadrature up to third order polynomial exactly. So when I say exactly, it means that the truncation error is exactly equals to 0. We cannot do that if we use trapezoidal rule, because the error for trapezoidal rule is not equals to 0. Now this is where it is important for me to explain that this condition, where I say you can actually perform this integral exactly by evaluating the function at minus 1 over square root 3 and 1 over square root 3, only applies if your a1 and a2 is equals to 1, and if your points x1 and x2 are chosen in this form. This is because when we derive our a1, a2, and x1 and x2, we have assumed a third order polynomial basis function. So for any general third order, it should be fine so long as the x1 and x2 are taken at minus 1 over square root 3 and 1 over square root 3. So in the next part of this lecture, I'm going to show, or I'm going to prove that this condition is exactly satisfied, meaning that this sentence here where we can say, or where we say we can integrate exactly up to third order polynomial using only 2 points, is accurate. Okay, so we have already shown that if you have a third order polynomial, you can basically evaluate the integral to be exact if you evaluate the function at these 2 points over here. Okay, this is provided that the limits of the integral is from minus 1 to 1. So can we really show that this is indeed true? So let's give a generic cubic polynomial. In this case, fx is equals to ax cubed plus bx squared plus cx plus d. So if you do this integral and you evaluate it from minus 1 to 1, this can be performed easily, where you get this particular expression over here. Now when you sub in the limits of 1 and minus 1, you will end up with this expression. So we know that this is the exact solution of this integral here if we evaluate the cubic polynomial like this. Now if you use a 2-point Gauss Legendre quadrature, we will write the same integral as a1 f at x1 plus a2 f at x2. So we already know that a1 and a2 is equals to 1. So in the end, we are just going to evaluate f at x1 plus f at x2. So for f at x1, what is f? This is your function f, which is the function that you want to integrate. So you would have a, your x1 would be minus 1 over square root 3. So you have minus 1 over square root 3 cube plus b minus 1 over square root 3 square, and then you have the c term, and then you have your d. So this would be f at x1. And then you have f at x2, where you have 1 over square root 3. So again, you have a cube plus b. So you have a positive term right now. And then you have a c, and finally you have your d. So because of the negative sign and positive sign, and because these are powered of odd numbers, these two will eventually cancel off. And from here you can show that this is eventually equals to 2b over square root 3 plus 2d. And if you compare to the exact solution, this proves that by using two-point Gauss quadrature, you are able to obtain an integral of a cubic polynomial up to if you use 2 point, you can perform exactly the integral of a cubic polynomial. Now, this is also what I've mentioned in the earlier part of this recorded lecture, which is if you're going to change the number of points that you choose, then the weights that you have derived and the points that you have derived when you assume 2 Gauss points will not be valid anymore. So every time you want to change n, the weights ai and the point xi will also change. So in this case, you will have to go and derive again what are the corresponding values of a and what are corresponding values of I. Fortunately for you, if you want to use Gauss quadrature, i.e. if you want to evaluate this particular integral for any given function fx here, someone else have actually done the derivation for you, and these are usually available in a lot of the mathematical handbooks out there. Okay, so this table here is the table of Gauss weights and Gauss points. So Gauss weights refer to the coefficient ai here. So some table will use wi, but for our unit, call it ai. And xi represents your Gauss points. Okay, so although in principle the Gauss Legendre